The destruction of a vessel on the open ocean is rarely an instantaneous event. For the steamship City of Cairo, the fatal blow came as a deliberate two-strike attack meant to finish the ship and send its entire payload to the seafloor. When the second torpedo struck the stern, the impact sheared through the aft compartments, sealing the fate of the vessel and everything locked inside its cargo holds. As the hull fractured and slipped beneath the surface, it carried a massive fortune with it. An estimated 100 to 122 tons of silver rupees, packed into thousands of boxes for government use, vanished into the dark water and began a long fall into the abyss, far beyond anything engineers could reach in 1942. The loss occurred on November 6, 1942. The City of Cairo was operating as a mixed cargo and passenger vessel. It was navigating a vast ocean transit alone, outside the protective screen of a naval convoy. With no escort destroyers to hold an acoustic and visual perimeter, the ship had nothing but distance and isolation for protection, leaving it completely exposed. The ship's engines burned smokily, generating a continuous plume of exhaust that painted a high profile against the clear horizon. This physical signature betrayed the position of the ship to a German submarine prowling the surface. The U-boat closed the distance, guided by the smoke trail, until the unarmored merchant vessel was close enough to strike. The attack began with a single torpedo. The weapon ran true and detonated against the lower hull of the City of Cairo. The initial explosion violently breached the steel outer plating and flooded the immediate compartments. Tons of seawater rushed into the void spaces, instantly stripping the ship of its forward momentum. Even with seawater pouring in, the steamship stayed afloat. Internal bulkheads absorbed the shock and contained the flooding just long enough to keep the superstructure up. The submarine commander then initiated a deliberate operational pause. For roughly 10 to 20 minutes, accounts differ. The submarine held its fire. This delay was a calculated allowance, providing the crew and passengers the narrowest possible window to abandon the dying ship. Lifeboats were lowered into the open ocean as the crippled vessel settled deeper into the water, its deck angling dangerously as the flooded compartments pulled the bow down. The evacuation proceeded under the shadow of the waiting submarine. During this agonizing window, the silver never moved. Sealed deep in the holds, it was far too heavy and far too late for lifeboats. The crew could only save themselves, leaving the treasury locked inside the sinking ship. Once the lifeboats were clear, the submarine resumed the attack to finalize the destruction. The U-boat fired a second torpedo. This weapon was aimed directly at the stern. The resulting detonation delivered a massive kinetic shockwave through the aft section of the ship. The structural integrity of the City of Cairo, already severely compromised by the first blast and the highly uneven distribution of internal floodwater, finally reached its absolute limit. The immense twisting forces finished the ship. Later surveys would show the wreck resting in two main sections on the seabed. With the stern torn free, it lost its last reserve buoyancy and dropped first. The bow lingered only moments longer before floodwater and cargo hauled it down after. What remained of the steamship began a long, irreversible descent. Deep inside the sinking wreckage, the 100 tons of silver rupees remained locked in their crates. The currency was completely intact but rapidly moving beyond all human access. The ocean swallowed the broken ship, pulling it down into total darkness. The survivors in the lifeboats were left adrift on the surface, while the City of Cairo vanished below with a staggering fortune still locked inside its holds. 16,896 feet below the surface of the South Atlantic, the physical laws of the ocean change. At this extreme depth, the environment becomes deeply hostile to modern engineering. The water column exerts an unimaginably heavy structural load on any object descending from the surface. This is the deep ocean pressure envelope, a zone where even 6,000-meter class deep water robotics can see failure rates climb and operating margins collapse. In this black, near-freezing thermodynamic regime, machinery can still work, but every hour is paid for in leaks, faults, and lost time. The extreme hydrostatic pressure at 16,896 feet attacks every seam, seal, and fluid system on a remotely operated vehicle. At the surface, hydraulic compensators are designed to balance internal fluid pressure against the external weight of the ocean. As the vehicle drops deeper into the water column, the ocean drives those compensators to the end of their mechanical stroke until they bottom out. Once external pressure exceeds the design rating of the components, the ocean starts forcing its way past primary seals and into systems that were never meant to see seawater. Beyond defeating the structural seals, extreme pressure can alter the way fluids behave inside the machinery. Under thousands of pounds of force per square inch, hydraulic systems may suffer higher losses and slower response as fluid properties shift and internal clearances tighten. The result is less crisp control in the arms and thrusters, more heat, and more power draw just to hold position in the dark. Every solid component on the vehicle is subjected to severe physical compression. The hollow syntactic foam blocks used to keep the heavy titanium vehicles positively buoyant begin to compress under the immense load. As the foam physically shrinks, it loses its displacement volume. The vehicle becomes progressively heavier in the water, straining the massive lifting umbilical that connects it to the surface ship and altering the delicate flight dynamics of the machine. The primary electrical housings, typically forged from high-strength titanium or thick aerospace-grade aluminum, physically deflect inward. Even microscopic imperfections in the metal or the synthetic rubber rings provide a direct pathway for the ocean to invade the dry electronic spaces. Operating a machine at 16,896 feet means accepting an unprecedented rate of continuous machinery breakdowns. The remotely operated vehicles must survive a downward transit that takes several hours just to reach the seafloor. During this long, slow descent through the water column, the temperature plunges toward freezing while the structural pressure climbs relentlessly. This extreme thermal and physical cycling stresses every single mechanical fastener, glass dome, and wire connection before the real work even begins. When the vehicle finally reaches the seabed, it is already operating in a severely degraded state, fighting simply to survive the environment. Systems that passed every rigorous diagnostic test on the deck of the surface ship will inexplicably fail once they cross into the deepest pressure gradients. To maintain salvage operations in this lethal thermodynamic environment, engineers cannot rely on factory-standard equipment. The standard tools suffer immediate, cascading structural failures. To survive the deep ocean pressure envelope, the engineering teams must push their structural tolerances to the absolute maximum. But before the engineering team could even deploy their modified robotics against the crushing depth, they first had to find a target in a featureless void. A massive steel hull shattered into two pieces on the seafloor should produce a highly reflective, towering acoustic signature on a digital sonar display. Instead, the geometry returned to the surface ship looked mathematically completely wrong. In 2011, a modern salvage expedition deployed to a coordinate 480 miles south of St. Helena. Their objective was to scan a vast, entirely unmapped stretch of the South Atlantic Ocean floor. The designated search area was incredibly large, covering a jumbled subsea terrain twice the size of London. Navigating a heavy survey vessel over this much territory while towing a fragile sonar array at the end of miles of heavy wire cable is a slow, methodical process that requires absolute precision. The operators on the surface ship had to constantly adjust the altitude of the heavy underwater array, carefully threading it just above the dangerous ridges and deep canyons to maintain a clear acoustic picture. They were looking for a needle in a massive geological haystack, trying to differentiate man-made metal from chaotic natural rock. When the acoustic waves finally washed over the prime coordinate, the digital return was dangerously deceptive. The expected target was a massive steamship loaded with heavy cargo, but the sonar painted an anomaly that lacked the sheer height and the sharp acoustic reflectivity of an intact shipwreck. This mathematical discrepancy was a geometry trap, created by acoustic mud masking. When a massive steel structure plunges into the seabed and breaks its spine, the violent impact digs a massive crater. The heavy sections settle deep into the impact zone, instantly losing their towering vertical profile. Over the course of nearly 7 decades, deep ocean sediment settled without pause, burying the fractured sections of the hull under a dense layer of silt. This thick blanket of mud fundamentally alters how sound waves interact with the object. Instead of striking hard steel and bouncing back a sharp, highly energetic signal to the listening sensors on the surface, then the acoustic energy is absorbed and scattered by the heavy sediment. The silt, muffled sonar return smooths out the sharp lines of the superstructure, blending the man-made wreckage into the natural geology of the surrounding ocean floor. A sunken steamship essentially camouflages itself as a series of low, uninteresting geological bumps. The acoustic shadows, which usually indicate the height of an object standing off the bottom, were critically shortened by the deep burial. On the surface, the digital data suggested the target was simply too small and poorly reflective to be the missing vessel. Standard survey protocol would dictate logging the anomaly as a geological false positive and moving on to scan the rest of the massive grid. Time on the open ocean is highly expensive, and deploying deep water equipment to investigate every weak sonar return is logistically impossible. However, the salvage leadership made a highly counterintuitive operational decision. They evaluated the mechanical physics of a fractured hull resting in deep ocean sediment and concluded that the mud was actively hiding the true mass of the ship. They suspected the violently broken spine of the vessel had reduced its profile, while the heavy cargo had dragged it deep into the soft sediment. They made the call to stop the wide area search and launch their camera-equipped robotics directly at the dubious sonar contact. Sending the vehicles down into the deep ocean pressure envelope meant committing massive resources to investigate a sonar contact that looked too small to matter. The long drop alone burned valuable operational time on a hunch that defied the immediate digital readings. As the cameras finally broke through the total darkness and illuminated the sea floor, the team verified their hypothesis. The low, muffled sonar bumps were not natural rock formations. They were the shattered, heavily buried remains of the lost steamship, packed with the target cargo. The decision to dive proved correct and confirmed the target, but remaining on site meant subjecting the underwater vehicles to a brutal environment that immediately began tearing the systems apart. The engineering team faced a brutal operational choice. They could either retrieve their failing machines for complete, time-consuming overhauls, or they could hot-fix critical components on the pitching deck and force the same degrading equipment straight back down. At this extreme depth, standard protocols collapsed. The salvage effort became continuous system attrition, triage, rapid swaps, and improvised patching, just to keep core functions alive, dive after dive. Every time the heavy tether hauled the remotely operated vehicle back to the surface ship, the engineers discovered new, unprecedented structural failures. The deep ocean pressure envelope relentlessly breached standard seals, flooding electrical junction boxes with freezing salt water and severely seizing complex hydraulic manifolds. Heavy steel pins were sheared, titanium housings were physically warped, thick synthetic wiring harnesses were crushed flat, causing highly unpredictable electrical short circuits that cascaded through the robotic control systems. Under normal salvage conditions, any one of these severe faults would ground the vehicle for days of careful, methodical repair. But halting the dive program meant losing the narrow weather window and abandoning the cargo entirely. Instead of fully rebuilding the shattered systems, the engineering team adapted on the fly. With breakdowns stacking up dive after dive, they turned the deck into a rolling workshop, swapping modules, reconfiguring what still worked, and improvising rapid repairs to keep the core functions alive. It was trial and error under a brutal clock. Fix what you can, launch again, and hope the vehicle survives one more descent. This aggressive strategy required the pilots to fly the vehicles with severe, known faults. The machinery was sent back down into the abyss while actively bleeding hydraulic fluid and suffering from intermittent electrical blackouts. The engineers had to resolve massive new technical faults on the fly to force their equipment to run non-stop for days at a time. They accepted that the standard deep-water robotics would never function at 100% capacity again. The goal shifted from operating a flawless machine to simply keeping the core extraction tools alive for one more descent. The operators learned to compensate for sluggish, half-functional robotic arms and thrusters that randomly lost thrust due to water ingress. Navigating a severely damaged machine around jagged steel wreckage required immense concentration, as a single control failure could entangle the vehicle and sever its vital umbilical cable. This relentless cycle of destruction and rapid rebuilding forced the technology to evolve in real time. The surface crew heavily modified the basic architecture of the vehicle, reinforcing the critical pressure vessels with heavy marine epoxy and custom fabricated brackets just to survive the long descent to the seafloor. They were locked in a constant race against the structural degradation of their own tools. The engineering team monitored the telemetry screens, watching the internal temperatures spike and the fluid reserves drain away as the vehicle fought the environment. Every hour spent on the bottom extracting heavy crates from the mud compounded the internal damage to the robotic systems. The heavy equipment groaned under the massive external loads, shivering with electrical ground faults and sputtering hydraulic pumps. The systems were pushed far beyond their rated limits, holding together just long enough to begin the most difficult phase of the operation, extracting the payload from the shattered hull. The mechanical signature of the weapon that ended the ship rested silently in the deep ocean sediment. Just beyond the shattered perimeter of the heavily buried steel hull, the salvage cameras illuminated a highly distinct piece of military hardware. The tail section of a German torpedo, ending in contra-rotating propellers. Finding that unmistakable hardware in the mud did not explain every detail of the breakup. But it did corroborate the simple truth of the loss. The city of Cairo had been finished by torpedoes, and this was the absolute physical proof of the loss event. But the primary objective of the expedition was secured deep inside the fractured remains of the steamship. Accessing the interior required the engineering team to navigate their heavy, damaged machinery through jagged debris fields. The vehicles were heavily scarred, their hydraulics already leaking as they fought the crushing pressure on the way in. Despite their severely degraded mechanical state, the heavy manipulator arms began the slow, methodical process of clearing the deep silt from the internal cargo holds. The heavy sediment had crushed the wooden storage crates over the decades, completely exposing the targeted payload to the open ocean. Tens of tons of silver rupees lay in massive, dense piles across the fractured decks and deep within the mud. Silver is an extremely dense metal, meaning a relatively small volumetric pile translates into a massive structural load for the robotic vehicles to lift. The manipulators had to carefully scoop the heavy currency, transferring the raw mass into specially designed steel recovery baskets. Every payload basket hoisted to the surface represented thousands of pounds of dead weight dragging on the main umbilical cables. The physical extraction was incredibly slow. The operators had to balance the massive weight of the silver against the dwindling structural integrity of their own machines. The sheer volume of the cargo required dozens of continuous rotational dives. Each operational cycle stressed the heavy winches on the surface ship and pushed the damaged underwater vehicles closer to total catastrophic failure. Extracting tens of tons of raw silver currency from the deep cold required absolute operational discipline. The pilots could not rush the extraction. If a heavily loaded basket snagged on a piece of jagged hull plating, the resulting dynamic shock could easily snap the primary lifting cable, sending the machinery and the payload back into the abyss. The silver rupees themselves had survived decades of deep ocean immersion largely intact. Unlike iron or low-grade steel, the precious metal did not rust away. Though many pieces could be darkened, stained, or encrusted after so long in salt water. As the heavy baskets broke the surface and were dragged onto the pitching metal deck of the surface ship, the massive scale of the physical recovery became clear. The engineering team had forced their dying equipment to rip a staggering fortune directly out of the deep cold. They systematically cleared the accessible cargo zones, pulling pile after pile of heavy coins out of the mud until the designated recovery targets were fully met. The grueling extraction phase pushed deep into 2013. The heavy lifting was finally complete, the holds emptied of their dense, silver payload. The surface ship was loaded with the massive physical weight of the recovered treasury. The complex salvage operation had defeated the extreme depth and the relentless mechanical failures. But closing the salvage record required one final operational protocol before abandoning the deep site forever. By September of 2013, the operational time window on the surface of the South Atlantic was rapidly closing. The seasonal weather patterns were beginning to shift, generating heavy, unpredictable sea states that pitched the recovery vessel violently. These heavy surface swells translated directly into massive dynamic loads on the primary lifting winch. Every sudden vertical drop of the surface ship threatened to part the umbilicals linking the vehicles to the control deck. The engineering team had already pushed their heavily degraded equipment to the absolute edge of catastrophic failure over months of continuous diving. They had successfully ripped tens of tons of silver rupees from the deep ocean pressure envelope, effectively balancing a massive financial ledger left open since the Second World War. But before they could completely disconnect from the deep site and sail away, a final maritime protocol had to be executed. The shattered halves of the massive steamship had been thoroughly surveyed, mapped, and fully documented. The designated cargo zones were completely cleared of the dense, precious metal payload. What remained on the deep seabed was a twisted, violently torn iron structure, slowly being consumed by the relentless thermodynamic forces of the deep ocean environment. The heavy sediment that had previously hidden the true shape of the vessel was now heavily disturbed by the massive industrial effort of the robotic extraction phase. Deep trenches and heavy track marks scarred the mud around the hull. Yet, despite the massive scale of the salvage operation, the underlying reality of the site remained unchanged. The broken hull was not merely an abandoned cargo container, it was a recognized maritime grave. To formalize the end of the extreme depth expedition and honor the staggering human cost of the 1942 sinking, the salvage crew prepared a final, non-commercial payload. They did not send down another set of heavy steel extraction baskets. Instead, they rigged the manipulator arms of their surviving remotely operated vehicle to carry a specially cast commemorative plaque. This heavy metal marker was designed specifically to withstand the crushing physical forces of the deep ocean without warping or corroding. The vehicle was deployed over the side, beginning its final, hours-long descent through the freezing water column and navigating the dangerous deep sea currents one last time. Reaching the chaotic, silt-covered debris field, as the pilots carefully maneuvered the battered machine toward a prominent, structurally secure section of the remaining steamship superstructure. Operating a machine heavily compromised by constant robotic breakdown required extreme precision for this final, delicate task. The heavy titanium arms extended outward, securing the solid plaque directly onto the rusted steel of the wreck. The inscription bore the ship's name and the words, "We came here with respect," and it remembered the more than 100 people who died, many after days adrift in open lifeboats. It was a stark, permanent monument placed in an environment completely devoid of all natural light. With the commemorative plaque firmly attached to the remains of the ship, the salvage team officially terminated their extreme depth dive program. The massive winches on the surface vessel engaged, hauling the battered robotic machine up through the water column for the very last time. As the heavy vehicle finally broke the surface and was locked down onto the metal deck, the expedition completely severed its physical connection to the seabed. The surface ship powered its main engines and turned away from the prime coordinates, leaving the shattered hull behind in the dark. The massive fortune of silver rupees would subsequently be melted down and sold, with proceeds reportedly divided between the United Kingdom Treasury and the salvors under salvage terms that were not publicly detailed. A small portion of the original cargo was retained for study and display. What had been unreachable in 1942 had been hauled back into daylight, showing that even extreme depth could be worked, at a cost. But the sea reclaims what is left behind. The deep ocean currents immediately began to smooth over the massive extraction craters, raining heavy silt back down onto the newly disturbed wreckage. The SS City of Cairo remains permanently entombed in the deep cold. Its cargo recovered, but its steel grave forever sealed by hydrostatic pressure.